AQA A Level Physics, Newton's laws of motion. Okay, this is what the specification says, which is not very much, but there's a bit more to it than that. However, you should have done this really at GCSE. There's not much more from GCSE that you need to know at A level, but you need to have a good understanding of what Newton's laws of motion are and where you might use them, where they would be applied. So Isaac Newton, very clever bloke. One of his books, Principia, the principles of natural philosophy. Basically, if we know the mass and the position and the velocity of an object now, and we know what forces on it, then we can calculate its position and velocity at any time in the future. You can predict where it will be and how fast it will be moving at any time in the future. Without Newton's laws of motion, there wouldn't have been an industrial revolution. We wouldn't have been able to build all these amazing machines. Now, Newton didn't do it on his own. In fact, Galileo was pretty close, and he built on the work of people like Galileo and Kepler and lots of other scientists, but he brought it all together and made them laws of motion and published it in a book. Okay, so Newton's laws of motion are very important. Now, Newton's first law: an object will remain at rest or traveling at a constant velocity unless acted upon by an external resultant force. So the cup on the left, there's two forces acting on it which cancel out, so there's no resultant external force, and it's at rest. It is stationary, it's not moving, it's in equilibrium. The aeroplane, there's four different forces acting on it: thrust and weight and lift and friction, but all of these forces cancel. It's moving at a constant velocity. There is no external resultant force. It's in equilibrium, a dynamic equilibrium. Okay, so basically, if an object isn't moving, or if it's moving at a constant velocity, then the resultant force is zero. Okay, so if something's stationary or going at a constant velocity, then I call it F res, the resultant force is zero. Newton's second law is, well, if the resultant force isn't zero, what will the object do? It will accelerate. Now, the actual wording of it, if you haven't done momentum yet, then we'll worry about momentum in a couple of videos' time. But if a resultant force acts on an object, then it will produce a rate of change of momentum. Its momentum will change, and the change in momentum divided by time, the rate of change of momentum, is directly proportional to the force and in the same direction. That's Newton's second law. So F is delta mv over t, which basically boils down to F equals ma. Now, strictly speaking, F equals ma is not Newton's second law. It is from Newton's second law, but it is the equation you're most likely to use. But don't forget delta mv over delta t. There's a lot of situations where we're going to use that one. So, and again, F res equals ma. Remember that it's the resultant force. There may be several forces acting on the object. It's the resultant force that we're interested in. Very simply, three cars here. The one at the top is in equilibrium horizontally. Thrust and friction are equal and opposite. If the thrust gets bigger, then there's a resultant force forwards. The car will accelerate. If the friction is bigger, there's a resultant force backwards and the car will decelerate. Notice that the resultant force is opposite to the direction that the object is moving in this particular case. Let's bung some numbers in. A car's engine produces a thrust force of 10,000 newtons. The mass of the car is 1,200 kilograms. If the acceleration of the car at that instant is 3 meters per second squared, calculate the friction force acting on it. Pause the video, have a go yourself. Answer in 3, 2, 1, and there you go. So F equals ma. So thrust minus friction equals ma. Bung in the numbers, 6,400 newtons. Here's another one. A water bottle is half filled with water, giving it a total mass of 1.5 kilograms. The air inside it is compressed. When it reaches a certain value, it pushes the water out and the rocket lifts off. And at the moment of liftoff, its acceleration is 12 meters per second squared. Calculate the thrust force produced by the ejected water at liftoff. And then I've put this thing at the end. Discuss how the acceleration of the rocket will vary in the seconds after liftoff. I suggest you pause the video and have a think and have a go at this question. And my answer, 3, 2, 1. So first of all, now T minus mg, thrust minus the weight of the rocket, equals ma. Remember that. That's a little tricky thing which comes up in AQA multi-choice questions quite a bit. Don't forget the weight of the rocket. And if you work that out, 32.7 newtons. A number of factors are involved which will have different effects. Now, the decreasing mass of the rocket. Now, I know that the specification said where the mass is constant, but this is the kind of thing you should be able to figure out. As the rocket loses water, then its mass will get smaller, so that the force acting on it will have a bigger effect. However, as it speeds up, then the air resistance force will get bigger, and the thrust produced by the water coming out will get less as the pressure of the air gets less. So what will happen will be a combination of these effects. Eventually, the rocket will slow down and stop, and then it'll fall down to the ground. But what happens before then is quite interesting. And what happens, I don't know. But I am aware of the physical principles involved, which will tick, 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 get me marks. An experiment you should do is to verify F equals ma. So you have a mass, a trolley, and you pull it with a force using a mass and a pulley, and you measure its acceleration. Different things you could do. You could do it over a certain distance. Its velocity at the beginning is 0. Its velocity at the end, you use a data logger to get the velocity, and then v squared minus u squared equals 2as. You can do a friction compensated slope. So if you tilt the slope very, very slightly, a couple of degrees, and that compensates for friction, or you could do it using an air track. The total mass of the system should stay the same. So what I do is I have masses on the trolley, and I take them off the trolley and put them on the thing at the end of the pulley. So the total mass of the system stays the same. And then obviously the mass is going to fall and hit the floor, and the distance that it falls needs to be at least as big as the distance that the trolley accelerates over. If you think about it, it should be pretty obvious. But you should be familiar with this kind of experiment here, verifying F equals ma. Newton's third law. Now, for every action, there is an equal and opposite reaction. I don't particularly like that, even though it's quite close to what Newton actually wrote. I prefer, if a body A exerts a force on body B, then body B will exert an equal and opposite force on body A. So the cup is pushing down on the table is pushing up on the cup with an equal and opposite force. We call this a reaction force. It's there as a reaction to the first force. So forces come in pairs. Here are some more examples. Okay, so starting top left, imagine you're that person on a skateboard, and if you push the wall pushes you, and what are you going to do? Okay, top middle, the force on the bullet pushing the bullet forward as the gun is fired, there's a force on the gun pushing it backwards. If you don't hold the gun firmly, you could break your wrist. Top right, when you do thermodynamics, balls bouncing against, well, particles in a gas bouncing against the walls of the container, and there's a force on the particles, there's a force on the wall, and that produces the pressure. Bottom left, there's a gravitational force of attraction. The moon is pulled towards the Earth, and the Earth is pulled towards the moon, and these forces are equal and opposite. It's the same force, but as the mass of the moon is a lot smaller than the mass of the Earth, it has more effect. However, the moon's gravitational pull does cause the tides. That's why we have tides. Well, because of the moon's and the sun's gravitational pull. Lastly, the swimmer, bottom right. If you want to swim, what you do is you push water backwards and the water pushes you forwards. And the harder you can push water backwards, the bigger the force pushing you forwards. When we do momentum, we will come back to examples like this, but you will not get a question which is just about Newton's third law. It will be part of something else to do with momentum, or maybe a suvat or something like that.